Hey, let's learn about pointers in Unreal. As a quick review of pointers in C++, pointers are really just memory addresses. And they're an address that points into your virtual memory. And think of virtual memory as this big array of addresses that contains bytes, and it's effectively the RAM of your computer. There's a bit of an oversimplification because you can have more virtual memory than you do RAM, because it can store it on the hard drive and then load it into RAM and pages in and out. But effectively, when programming, think about it just as RAM that is loaded in memory, ready to go, ready to use. And Unreal pointers are really just your way of getting a handle to some object in memory, so an actor, and you're not really thinking about the raw bytes or addresses too much. Unreal does extend the concept of a pointer a bit. So in general, a pointer is going to have some memory address that points to a spot in virtual memory. But Unreal has the concept of soft objects, which we'll talk more about later, that can also point to a spot on the hard drive that may or may not be loaded. So it can use this to load something into virtual memory. So here I'm running a pointer test. To introduce you to pointers, if you have an actor that is a U class, it is part of a special garbage collection system that is built by the engine. There are various ways that you can hold pointers to other objects. You can have a raw pointer like this, where it's just a standard C++ and C pointer. And the fact that this is a U property will prevent this from being garbage collected, at least naturally. But there is also now a TObject pointer, which behaves very similar to a standard pointer, but is the preferred way for holding onto pointers, because in some contexts, like use structs that are in T arrays, this should always initialize it to null pointer, whereas a raw object pointer may not. There is also a TWeakObject pointer, and the weak means that this isn't going to be a reference that should keep the object around from being garbage collected. So weak specifically is related to garbage collection. And there's also the soft object pointers, which refers to not garbage collection, but whether or not an asset is loaded from the disk into RAM. So it's soft in that it might only be on the disk, but not loaded into memory. Then it may load and now be in memory and on the disk. So we'll explore that in a moment. So we can deal with raw pointers like this. You commonly see this as function parameters or return types from functions. We can use TObjectPtr in place of this raw pointer, and it mostly just works. You can convert from a raw pointer to a TObject pointer like that by just assigning to the raw pointer. You can also convert back from a TObject pointer to a raw pointer by calling the get method. A TWeakObject pointer can also be initialized from a raw pointer. You can check if it's valid, that is, does it still point to something in memory? This will be true if it's still in memory, and false if the garbage collector has claimed it. The weak aspect means it doesn't provide a reference to the object as far as the garbage collector is concerned. The garbage collector is free to claim the object, and the weak object pointer won't exert any control over its lifetime. You can convert from a TWeakObject pointer to a raw actor pointer by calling the get method, similar to how we did with the TObject pointer. There is also the concept of a class pointer, so this allows you to point to the reflected class of something. So for example, here's an actor. We're not actually having a pointer to an actor, but its class instead. So this lets you do things like, say you wanted to spawn an actor of a certain class. You don't have the actor instantiated, but you have its class. So you can pass TSubclassOf around to determine how to spawn certain actors. There's also a soft class pointer. It's a similar thing, but loading a class loads things that it references. Perhaps you don't want it to necessarily be loaded unless it actually needs to spawn. So you could have a TSoftClass pointer of an actor and load it as you need it. The way these soft class pointers or soft object pointers work is they have a function called isNull, and you can read this. It says test if this can ever point to a live object. So the way I interpret this is, does this currently have a valid path, basically? And if it has a valid path, then it can be loaded. So it could potentially point to a live object or a loaded object. So could it be loaded? You can see here that it has a path, asset path under game exploring pointers async load actor. So it can load, and now we can use the isValid function, similar to the weak actor pointer or the TObject pointer isValids, to test if it's currently loaded into RAM. And here we can see that it is not currently loaded into RAM. So if we can load it and it's not currently loaded, there is a function to force load it right now. It's called LoadSynchronous, and this will block until it loads. So this can create a hitch if you don't do this during a load screen. Nevertheless, I'm going to force load it here. And now you can see that the class has loaded, and we log that. It's similar for TSoftObject pointers. So here I have my soft object pointer, and I want to know, does it point to a valid thing? Can it be loaded? And that is true. So if we look into here, we can see that there is a path exploring pointers async load data asset and test if it's loaded. So is it valid? And it is currently not valid. So you may think it doesn't make a lot of sense to have a soft object pointer. Like you can't really point to an actor in memory if it's not loaded, right? This is more for things like data assets, which are just like objects that hold data. So you may point to a data asset, but not have it loaded because you don't want to bring all this data into memory. And so in this case, we're going to load it, but we're going to do it asynchronously since it can be loaded and it's not currently loaded. If I try to get it before the read, we can see that it is null. So what we're going to use is a StreamableManager to stream this in asynchronously. And note, if you're testing this in the editor will have assets loaded for you just as part of the editor loading. So you might want to try this type of thing in a standalone game. That's what I'm running right now. Anyways, so we get this StreamableManager and we request an async load. The first thing we do is we provide it the soft object path. And then we create a weak lambda for a delegate, a streamable delegate. And this delegate will give us a callback when it has loaded. And so I have a breakpoint here. So when this loads, we will get this callback. And I can step over this. So it did not load. We're going to get that in a moment, but we'll continue. In fact, I suppose I will just put a breakpoint here. And I'm going to resume execution until we hit this. So I resumed, and now we are on a much later frame. So we can see, is the soft object pointer valid now? And it is. That means it async loaded. Because we look up here, the is valid check is it loaded? And the null check is can it be loaded? And so we check is it null? It is not null, and it can be loaded. So we ask it for the object this time, which we saw right here, it returned null, but now it returns a valid object. And then we log that. Now it's important to know there's this concept of a streamable handle. So if I go to the streamable handle, it is a shared pointer, which we'll get to in a moment, but effectively this handle keeps it in memory. And so I have a CVAR here to basically clear out the handle so that it can unload. So I will flip the CVAR to false so we can run it again and see the opposite behavior. But since we clear out the streamable handle here, we continue and then wait a moment. I can then run the test again and step down to where the soft object pointer is again. And we can see if it unloaded. So it did unload. It is now no longer loaded. So we will try that again. We're going to test it. The get method returns null. We get the StreamableManager, ask it for an async load, and then I'm going to resume and wait. And now that we've waited, we can test, is it valid? So is it in memory? It is in memory because it just got done with the async load. The path is obviously not null because we kicked off this load. And now our call to .get turns the object again as expected. But I've set this to false so we don't clear the streamable handle. We're just going to step over that. And then we can wait some time and run the test again, and it should still be in memory this time, since we still have a streamable handle that's active. Alright, I paused the video and waited a few minutes. We can run the test again. And now that we're back at the object, we can see, can it load? Yes, because the path didn't change. But is it still loaded? And that is true because our StreamableManager is still around and keeping it in memory. So lastly, there is one more class of pointers. What we were looking at here are pointers related to garbage collection and async loading. But there is also a shared pointer system that is completely separate from the garbage collection system. Unreal also has smart pointers as part of the engine. That is, it has shared pointers and weak pointers, and also unique pointers. The standard template library in C++ also has a smart pointer system, so you may be familiar with the paradigms from there. But to demonstrate that, I've created a very simple class, and it just has a constructor which logs the debug name, and it has a destructor which logs when the destructor runs. So if we step down here, we can see how these work. I'm using scopes with logging to demonstrate lifetimes. There are two ways smart pointers work. UniquePtr is perhaps the most simple. The main thing it does is it automates the delete operator. So you can new an object into one of these, and when it leaves scope, the destructor of the UniquePtr will call delete on the nude object. So that way the memory cleanup is automated. There can only be one handle to a UniquePtr. You can't have two UniquePtrs pointing to the same thing. That violates the ability for it to clean up. Should you want something like that, that is where shared pointer comes in. Shared pointer can have multiple pointers all pointing to the same allocated memory. This memory is allocated generally on the heap, and the memory is kept from being deleted as long as there's at least one reference to it. So these shared pointers increment effectively something like a control block or reference controller every time a new shared pointer points to an object, it is incremented, and it keeps track with how many shared pointers there are. And the deletion of memory will not be automated until that reference count gets to 0. Weak pointers work with shared pointers, but they don't increase that reference count, at least not in a way that will prevent this from being deleted. So if you have one shared pointer and one weak pointer, if the shared pointer leaves scope, but the weak pointer is still around, it won't prevent this from being deleted, and the weak pointer will return null pointer when there is no more memory. So to demonstrate that, let's check out the logging here. Right here it says starting outer scope, and we see that in the log. And then we say that we're making a shared pointer, and you can make a shared pointer with this function called MakeShared. It's like a new operator, and you can pass into it the arguments for the constructor. For example, here we're passing in an f string. We're implicitly constructing it, my text literal, and this allocates a shared pointer for us on the heap. And we can assign this shared pointer to another shared pointer to increase the reference count. So if we inspect the internals of this, you can see the shared reference count is up to 1 right now. After I assign that and inspect it again, the reference count is now 2. And as we stepped out of the scope, this is now no longer in scope. So we can re-inspect the reference count. You can see it's down to 1. And then as we step out of scope here, nothing has happened yet. And as we leave this scope, this variable will no longer be relevant in Cloud's destructor, which should free the memory, as the reference count should go to 0. We can see here that a destructor was logged, and since this is out of scope, I can't inspect it anymore, but it effectively went to 0. And so the cleaning up of memory was automated. Now, this MakeShared thing is one way to construct a shared pointer. However, if you wanted to call the new operator manually, you still can with this function called MakeShareable. You just need to be careful in that you do not pass any existing memory into a MakeShareable, and that there needs to be only one of these that is managing this new pointer. Otherwise, you could run into conditions where it thinks the reference count is 0, but there's still something referencing it. So just be sure that you only do this once and you don't use this pointer anywhere else in a similar situation. If we look at the shareable, you can see that it should have a reference count of 1 once we initialize it. Now that we've initialized it, we can look at the reference count and see that it's up to 1. And as this leaves scope, that destructor was now called, and that was all automated. The way a weak pointer works is we'll step into this scope and we'll make a shared pointer here, so MakeShared, and then we'll assign the weak pointer to that shared pointer. And if we look at the view now, you can see there is 2 weak references and only 1 shared reference. I believe there's 2 weak references, as the original one may also count as a weak reference. I noticed that there's generally 1 for that. Anyways, so we have a weak reference now, and we can see here that the weak pointer is valid. We logged it right here. Now, as we leave this scope, the shared pointer is going to go out of scope. And so the weak pointer reference was still valid while we were in the scope. That is what that last print was. And now we are leaving this scope, so it should destructor and a destruct. But we still have our weak pointer, so we can print out if it's valid. And now the weak pointer is not valid. If we look at the raw view, you can see that the shared reference count is 0, but it still has 1 weak reference count. And so that is how weak pointers can be used. Weak pointers are useful in that they don't create a strong reference on the shared pointer, so it allows the shared pointer to be cleaned up. One common issue with shared pointers that isn't present in the garbage collection system is that if you have a shared pointer that references another shared pointer, and that other one also references the original shared pointer. So if you have shared pointer A, shared pointer B, pointing to 2 different objects, and each of those objects point to each other, you can create an island that basically keeps itself in memory. And so you need a kind of like tree that doesn't create cycles if you want shared pointers to work correctly. And in garbage collection, I believe these islands can be claimed entirely. So when dealing with shared pointers, do keep that in mind, that it's not exactly the same as a garbage collection system, and you need to make sure that your pointers can in fact clean up correctly. And often what you can do is introduce weak references or weak pointers so that that is the case. As far as unique pointers go, here we have a makeUnique, which is like MakeShared. This is like calling a new operator on a plain CPP class. And so we've constructed this unique pointer, but unique pointers are not like shared pointers. You can only have one of them. And so if you want to assign a unique pointer to another unique pointer, you actually have to move it out of the original and into the new. So here, our unique pointer is scoped to this, but we're going to move it from here into this, just going to change its scope to be this scope. So now we've moved the weak pointer. We can see that it's there as the debug name. And if we look at the original one, it is now null pointer. So that is the effect of moving a unique pointer. And we log some state. You can see it was valid before the move, and it was invalid after the move, and the move pointer is now valid. Now, as we leave this scope, it should clean up the unique pointer. And there we go. The destructor was called. So you can see it was no longer tied to the original scope, it was tied to this smaller scope. And the last thing to mention is this TSharedRef concept. This is not in the standard template library of C++. This is an Unreal specific thing as far as I'm aware. And a TSharedRef is supposed to basically not be nullable. You can assign a null pointer to a TShared pointer up here, but for a TSharedRef, you need it to be basically not null pointer. And you can create TShared pointers from shared refs, and that works all well and good. Hey, real quick, let's discuss for declares, since you'll see these throughout the engine. Like normal in C++, you include the files that you would use. So here we need to include TObjectPtr. But sometimes you run into a situation where you don't really need to know much about the file. You only need to know that it exists. Like here, I'm using a player controller and a game state, but really I'm only holding pointers to those, so I don't actually need specifics about them. And so instead of including the game state, I can actually for declare it like this. And this is basically saying there's a class with this name that exists. And so that lets me use a pointer to it without really knowing much about what it points to. There's another variant of for declare where you just type class in front of where you use it. And you can do that in functions like this. Or we can for declare it at the top, so it kind of looks like an include, but it's more lightweight, and just use that down here. And then now in the CPP file, so this was in the header file, and now in the CPP file, instead of including it in the header file, I include it in the CPP file, and this will let me use the functions on those custom types. Like for, in this instance, they return a string, so I need to know a little bit more than just a pointer. But because I included here, if something changes in this header file, it'll only recompile the CPP file. But if I had included it over here, and something changed in that header file, then anything that used this header file would also need to recompile. So you save compile times by for declaring when you can. And also, it allows you to have like circular dependencies. So I could have the game state using the player controller, and the player controller using the game state internal to those, if in their header files they just for declare each other, but in the CPP files where the functions are actually defined, they include each other. In that case, there's not a circular include dependency. Each one just includes what it needs. And so that's a crash course on for declares. If you can use them because they speed up your build time and make things more flexible. But otherwise, you'll just need to use a full-fledged include if you need specifics about the type in that particular file. And I hope that makes sense. There's quite a few different pointers in Unreal, but just keep in mind that you have the garbage collection system, which is dealing with these types of pointers. You have the more classical C++ memory management, which is smart pointers. So we have weak, shared, and unique. And then you also have soft pointers, which refer to asynchronous loading. So hope that helps. Let me know if you have any questions, comments, concerns, or even corrections in the comments below. And until next time.